Hi all. In this video I want to look at the addition of HX, a hydrogen halide, to asymmetrical conjugated dienes. We know that these are conjugated because the two double bonds are in a row and we get a row of 4 sp2 hybridized carbons. It's asymmetrical because if we react the double bond on the left with HBr, we should get a different set of products than if we react the double bond on the right with HBr. Let me show you how I would solve each of these reactions. So here I label the two double bonds for the first reaction as A and B, and let us read the problem. Draw the products and circle the major product if there is one. Do not draw identical products, or if you do, identify which are identical. For this particular type of problem, adding HX to conjugated dienes, it's very important that you as a student understand what is the professor looking for. Are they looking for all of the possible products? Are they looking for maybe two products that come from the same carbocation? Or are they looking for that one major product based on the temperature and which double bond is most reactive? So there is a lot to digest. Here, basically I'm asking for all the products and then identify that one major product. To solve this type of problem, it's multi-step, and for the first couple of times we should go slowly and do every step. As you get more familiar with this reaction, then you could take shortcuts and maybe even be able to draw all the products without doing much scratch work. The first thing I'm going to do is to draw the carbocation and its resonance based on each double bond. So if I have this HBr and I'm going to use double bond A, you know what happens. We're going to grab that proton, kick out Br, and we get our initial carbocation. Our initial carbocation looks like this, and there's a plus sign there. Now we know that these are allylic, right? Allylic carbocations, and allylic carbocations have resonance. The resonance here, you move the double bond towards the plus charge. We shifted the double bond. We have resonance arrow here, and we have this new carbocation. But these are resonance structures of each other. So the real molecule looks like this. It's called the hybrid structure, or the hybrid resonance. And we have 1.5 bonds here, 1.5 bonds here, and a lot of times people just draw the plus sign in between those two carbons. So the reason why I tell you about this is that, again, you got to remember that these are resonance. There's only one carbocation represented. It's this carbocation, but you could represent it two different ways. This is the carbocation that's coming from double bond A. So can you draw the carbocation that's coming from double bond B? I'll represent the movement of electrons using this purple arrow. And why don't you pause the video and draw the two resonance contributors. So here I have the two resonance structures representing the carbocation if double bond B is used. Again, it is allylic. That's why I put the plus charge here and not here. And I also drew the resonance hybrid. Now, normally I wouldn't ask for that, the hybrid structures, but here I just want to, again, really emphasize that we are only dealing with two carbocations for this reaction. This carbocation and this carbocation. But obviously we could represent it with these Lewis structures. All the possible products, they're coming from these 4 representatives of carbocations. So why don't we draw those, and I'll use this one as an example. What happens is, we kicked out a Br, and well, here, I can't use this structure because I already drew an arrow on it. So let me actually grab this carbocation It's very easy. We are just putting the bromine where the plus charge is. So if we have this carbocation, I am giving you the mechanism. It's just kind of jumbled. It's not all in one line, but we did produce Br minus, and here's your plus charge, right? And opposites attract, and our product that's coming from this carbocation, or this resonance contributor, looks like this. Okay, so that's product number 1. Can you pause the video and draw the other 3 products? Then we're going to have to pause and analyze if any of those 4 are identical. Alright, here are the 4 possible products. These are made, but some of them are minor products, and we have to identify the major product. Where are these 4 coming from? They're coming from the carbocations. That came from here, this came from here, this product came from here, this product came from here. You know, these are all, what, allylic bromides. Okay, so that takes care of drawing all the products, but the problem also asks to identify the major product. Oh, the other thing is that none of these, a quick check, none of these are identical. Something that's very useful to remember is the major product has to come from the more stable carbocation. So here's where language is very important. When I say the major product has to come from the more stable carbocation, I'm actually comparing these two, and I'm not looking for the most stable carbocation out of these 4. How you can remember that is you're choosing which double bond gives you the more stable carbocation. Is it A or B? So how do we do this analysis? Let's take a look at the carbocation resonance structures that come from double bond A, and we get these 2 resonance structures. The first one is secondary allylic, and its resonance is tertiary allylic, right? Tertiary allylic type of carbocation. Over here we have a secondary allylic carbocation, and over here we have a primary. Okay. When I say the major product has to come from the more stable carbocation, you're not choosing one of these structures. You're choosing a set. And here we see that A is the winner because a combination of these 2 contributors gives me a hybrid that is more stable than the combination of these 2 resonance structures and this hybrid. But you know, you can't really do the analysis by looking at the hybrid structure. You want to break it up and look at the contributors. So the conclusion from this analysis is A is the double bond we should use, and a better way to say that is A is the more reactive double bond. So here's the rub. If the problem didn't have temperature, and I asked draw all the products and circle the major product or products, you would draw all 4 of these and you would say that these 2 are the major products. Now, you've seen from previous lectures or videos that you know these 2 as a 1,2 and the 1,4 addition. 1,2 and the 1,4 addition. What's the major product between these 2? Well, you would need temperature to decide that, because if this was run under very cold conditions, you would aim for the kinetic. Oh, this is very interesting. The kinetic product is always the 1,2 product. The thermodynamic product, if you ran this at a little bit higher temperatures, and I like to use the cutoff room temperature and above, you go for the thermodynamic product. Well, you go for the more stable alkene. Very interesting. I wasn't expecting this actually. Which one is the more stable alkene? Is it the 1,2 or the 1,4? See, the more stable alkene is here, the tri-substituted, the 1,2. The thermodynamic and the kinetic product is both the 1,2. I like to say that the initial carbocation is going to give you the 1,2 product, always, right? And the resonance will give you the 1,4 product. The 1,2 product is always going to be the kinetic product. But the thermodynamic product could either be the 1,2 or the 1,4. You have to analyze the final product. Let me repeat that. The 1,2 product is always kinetic. The 1,4 could be thermodynamic if the final product is more stable than the 1,2. But in this case, the 1,2 is also more stable. So regardless of the temperature, right, it would have to be this product right here is the one major product. Now, if I take a look at the temperature, I would tell myself, even before drawing all of this actually, that you want the what? It's 0 degrees or above. That's the thermodynamic product, the one that's more stable. I won't get into why. Higher temperatures, you aim towards the thermodynamic product. That was discussed in the previous video or lecture. When you get to negative 78, okay, you are going to aim for the kinetic. So we'll do the kinetic product here. Okay, so let me wrap up this reaction here. The major product is this. It's actually both the kinetic and thermodynamic product coming from the more reactive double bond. And this is the more reactive double bond right here because it gave a set of resonance contributors that's more stable than the set given by B. It's very subtle, but I am not looking for the most stable carbocation, right? The most stable carbocation is right here. It's a tertiary. But it is neither the kinetic nor the thermodynamic product. It neither leads to the kinetic or the thermodynamic product. It's actually the 1,2. Think about what we just did here, and think about our next problem. I'm aiming for the kinetic product, and that's guaranteed to be the 1,2. The 1,2 product is always the kinetic, and it could also be the thermodynamic, or the 1,4 could be the thermodynamic. So I'm aiming for the 1,2 product as the major product. I just don't know yet whether I need the 1,2 product from double bond A or the 1,2 product from double bond B. Do you want to try it on your own? See if you could draw all the products. Potentially there could be 4. Find the major product. Okay, I still want to go through our analysis of the carbocations, the ones coming from A and the ones coming from double bond B, and I get these 2 sets. And you know that eventually we're going to have to know which double bond gives us a more stable carbocation. They're all allylic. Okay, and the first one is what? It's a tertiary allylic. This one is a secondary allylic. For double bond B, our initial carbocation is here, and that is definitely secondary, and the resonance is secondary. Now, if you didn't get these carbocations, go ahead and make your corrections, and then pause the video and draw the 4 products that are coming from these 4 resonance contributors. And this was a good example also. We have our 4 potential products, but what do you notice about 2 of them? We didn't see this in the other example. In our first example, we had 4 different products. But here, do you notice that these 2 are identical? So either you cross one out, because I said up here, do not draw identical products. You don't want to mislead the person into thinking of 4 different products. Instead of crossing one out, let's just write these 2 as identical. Or I like to do something like that, I. Those are our 4 products, and yeah, we want the kinetic product. So this is 1,2. This is 1,2. This is coming from double bond A. This is coming from double bond B. This is a 1,4 product, and yes, Interesting. The 1,2 and the 1,4 product are actually identical. Do you see how they're identical? Now, I'm not good enough to be able to predict that just looking at the starting material. I literally had to draw these two out and then do my analysis which ones are identical, if there are any identical. Now, if I want the major product, I want to figure out which double bond is more reactive, which double bond gave me the more stable carbocation. And again, it's A, and that's just a coincidence. It doesn't have to be the one on the left all the time. So A is the winner. Right? We have a tertiary and a secondary, and we have a secondary and secondary. This is the winner. Because the temperature is very, very low, negative 78 degrees, I want the kinetic product or the 1,2 product. Again, 1,2 is always the kinetic. That's the major. It is the 1,2 or the kinetic product coming from the more stable carbocation. Not the most stable overall, okay? The stable contributor, stable hybrid. So you are analyzing, or you are combining both of these. I kind of like asking the problem this way because the student has an opportunity to get partial credit if they draw all the products without having to choose a major one, and then they get full credit if they choose the major product. So it gives them an opportunity to get points for drawing everything out, and then to get full credit they would have to identify the most stable carbocation and whether they're aiming for the kinetic product or the thermodynamic product.